Okay, this is the lecture video for Math 1100. We're in lesson 4.2, and in this section we're going to take a look at the Pythagorean theorem, which is a theorem that relates the sides of a right triangle. This is the symbol for right triangle, meaning that one of the angles is a right angle, 90 degrees. So what this theorem states is that the hypotenuse squared, which is what they have right here, they're calling it C. They have decided to assign a variable to each side. So based on what you see here, this theorem states the hypotenuse squared, which they're calling C, is equal to leg squared plus the other leg squared. And they're calling one of the legs B and one of the legs A. Or you can generically write it like this. If there are no variables involved, you can just find the hypotenuse, which is always located directly across from the right angle. If this is the right angle, just jump across to the opposite side, and that will be the hypotenuse. The hypotenuse is always the longest of the three sides. So in the formula, the Pythagorean theorem, it is kept by itself. Whether it appears on the left or the right side is irrelevant, just it must be on one side of the equation all by itself in its squared form. Notice that everything is squared in the Pythagorean theorem. And then the two shorter sides, each one squared and summed together, will be on the opposite side that you have the hypotenuse. Okay, so we're going to be using that as we go to solve for the missing side in a right triangle. Okay, in the first example that you see here, again, you always want to write the theorem or the formula down that you're using. We are using hypotenuse squared is equal to leg squared plus leg squared, known as the Pythagorean theorem. And that's because we're trying to solve a problem that involves the sides of a right triangle. In this picture, again, I was stating in the previous picture that we looked at that the hypotenuse can always be identified by just jumping right across from the right angle, and the side that's across from the right angle is the hypotenuse. So you want to know exactly which one's the hypotenuse. Remember that in this equation, it is kept on one side all by itself when you begin the problem. You can move things around from there, but when you're initially plugging into this theorem, the hypotenuse is on one side all by itself. On the other side, you'll have each of the legs squared and added together. So in this problem, it's going to be x squared. Okay, and then if you need to get assistance from your calculator, get mine. You can always press any of these numbers into the calculator as you go to square. Okay, so make sure that you know where the square button is on your calculator. So I'm going to be pressing in 40. Let me try turning it on. That might help. 40 raised to a power of 2. That's 1600. And likewise, any of these numbers that you can't square in your head, you can put it into your calculator. You would also press this in, which is equal to 81. And you're going to work this side all the way until you get to the point where you have a single number on one side. So 1600 plus 81 is 1681. Okay, now you're trying to solve for x, yet at this point you have x squared. So you need to know what operation undoes a square. What operation is considered the opposite of squaring? And that would be the square root. Taking a square root is we call it the inverse. It really means the opposite operation, is the inverse operation of squaring. So you have an item squared here and you want to undo that. So you're going to use the inverse operation, which is to take a square root. And if you're going to take a square root on the left side of this equation, you must also take a square root on the right side. Because with equations are considered balanced statements. So to keep it in a balanced state, you must always perform the same operation on each side. Now you make a decision on what kind of operations to do based on your desire to isolate this x. And you want to report the answer for x without any kind of power other than 1. So therefore, the decision to do this on both sides was because there was a square there. I wanted to undo that. And so I performed the inverse operation of squaring. Right now this is being squared. Opposite operation is to take the square root. Okay, hold on for 1 second. Okay, so in this section as well as the next section, you're going to be working quite a bit with square roots. Okay, so square root is how we undo this. That means when I say that this operation undoes this, that means it cancels it. And out comes the x. And then you can again get assistance from your calculator for any square root that you can't do in your head. So it would be second, call up the square root symbol, feed in the number that you want to take the square root of, close it, and the square root is 41. Okay, so finally you've gotten the answer for x. Okay, now moving on to this next example. Again, we know that we're going to use the Pythagorean theorem because we're trying to deal with the sides of a right triangle. And Pythagorean theorem is what controls that. It controls the relationship amongst the 3 sides. Write this a little bit more clearly. Okay, we happen to have one side that we don't know the value of, and you can call it x, or you can call it any variable you want. You must call it some variable so that when we go to plug into the Pythagorean theorem, which once again is hypotenuse squared is equal to leg squared plus leg squared. So one of these pieces is unknown. It happens to be one of the legs. Remember, the longest side, which will always be directly across from this right angle, is the hypotenuse. The other 2 sides of the triangle are called legs. So you have a leg running horizontally and you have a leg running up and down vertically. This leg that's running up and down is unknown. We do not know the length of it. We do know the length of one leg and we do know the length of the hypotenuse. Plugging it into this theorem, it would be hypotenuse, which is 37, squared, because that's what the theorem forces you to do, to the hypotenuse. Then we do know one of the legs. Theorem says to square it and then add it to the other leg squared. And that other leg happens to be the one that's unknown. Okay, now we're going to go to our calculator to get assistance with the squaring portion. So it's 37 raised up to a power of 2. One more time, 37. Then do the power key, raised up to power of 2, and that is 1369. Then we need 31 squared. Be 31, power key, square it, 961. Okay, then we're going to subtract 961, subtract 961. And that's because we want to get the x squared term by itself. Anytime, if you recall from the sections that we had when we were solving for equations. Whenever we're trying to solve for x, if there are any numbers that are being added or subtracted from your x variable, you need to get them on the other side. And that's what this step is about. So I'm moving this 961 to the other side by subtracting 961 here as well as here. So now it's gone, and all you have left on the right-hand side of this equation is x squared. And what you have on the left side would be 1369 minus 961. And that would be 408. Okay, and then again, the opposite operation, or what we also call the inverse operation of squaring a quantity, is the square root. Okay, square root is the opposite operation, and therefore it undoes the square. So this gets rid of this. This square root gets rid of that. If you're going to take a square root on the right side, you must also take a square root on the left side. Always do the same operation to both sides. Okay, so out comes the x because the square root has done away with that square. So out comes the x. And then again, you can go to your calculator to get help with what's the square root of 408. So second square root, dump the 408 in there, and let's round to the, let's see, it says to the nearest tenths place. So nearest tenths place, this is the number in the tenths place, the 1. Look at the number next to it, and if it's higher than 5, round it up. So this is going to be 20.2. And the unit that's in this problem, meters. So a couple of examples and a little background on the Pythagorean theorem. It is used for right triangles. The hypotenuse will always be the side across from the right angle. When you set up the problem originally, it will always be the hypotenuse squared and then both of the legs on the other side of the equal sign. Everything in its squared form, plus sign in between the squared legs. And then you will work to get the x squared by itself. So in this first problem, this was the easiest level of the Pythagorean theorem type problems. This had one less step than the problem after that, and that's because the unknown was the actual hypotenuse. So you didn't have to try and remove other numbers that were with it and get them on the other side because it was already by itself. When the hypotenuse is the thing that is unknown, all you'll have to do is square each one, add these, and take the square root. However, this problem presented an extra step, and that's because rather than us looking for the hypotenuse, as we were in the previous problem, this time one of the legs was unknown, and that's going to cause an extra step. Because once you plug everything in, you're going to have to take this number and move it away from the x, get it on the opposite side. So that was the extra step that this problem had. And then we still needed to get rid of the square like we did in the previous problem. Okay, now we move to another application where we're using the square root symbol or operation, and that's called the distance formula. And the distance formula is used for any 2 points that are not horizontally across from each other or vertically across from each other. Like for instance, let's say that I had a segment right here, and I'll just call this point C. And let's say that I had 2 points that were vertically aligned like this. In this case, when they're directly across from each other, if I was to ask you what is the distance, you don't really need to use the formula because you can just count the number of spaces. 1, 2, 3, 4, 5, 6. So that would be the distance right there. The distance from A to C. Or Another case where you can just count the spaces is when the two points are vertically aligned. These are horizontally aligned. They're right across from each other horizontally, and so I was able to count 1, 2, 3, 4, 5, 6 spaces to get from A to C, which is also considered the distance. Same thing here. Because they're lined up like this, you can count the spaces. 1, 2, 3, 4, 5. So the distance from here to here, from B to C, without using the distance formula, the distance is 5. However, if they are not horizontally arranged or vertically arranged, but rather on a slant, that is when you have to use the distance formula. Okay, so let's take a shot at that. Give me 1 second. Okay, so what you see here are 2 points, and let's see if these 2 points, why don't we plot them? Because if they are either horizontally across from each other or vertically arranged, stacked up upon each other vertically, we won't actually have to use the distance formula. Now, I'm going to do it both ways just to give you practice, but I just want you to see that if they are either in this arrangement or this arrangement, you can actually count them with your finger. So let's do like a little graph here. And let's see, if we were at 7, -7, okay, let's say that this is 7. 1, 2, 3, 4, 5, 6, 7. This will be 7. And then let's say this is 1, 2, 3, 4, 5, 6, 7. And this would be -7. So let's say we had a point right here at 7, -7, and then we have another point at 7, -3. And this would represent -3. Okay, this is the y-axis, this is the x-axis, and we're plotting points where this is the x and this is the y. So if I was going to plot this other one, here I just plotted x and y, and if I was going to plot this other point, it would be out 7, down 3. So it would be right there. Now, do you see how these are vertically stacked up upon each other? In fact, what you're really doing here is you're going from -3 to -7, and you can just count the spaces. It's just 1, 2, 3, 4 to get from here to here. It's just a distance. I'll just put D for distance, a distance equal to 4. Now I was able to get that answer because they were vertically stacked up. So because they have, and one way that you can tell that they're going to be vertically stacked up is when they have the same x coordinate but different y coordinates. That means you're moving out the same x distance, but you have different y values, which means that they are vertically arranged, and you're going to be able to count the distance. From here to here is 4 spaces. You can also put it into the distance formula, because even for the cases where you could possibly carry out a shortcut by just counting the distance with your finger, or you could take a shortcut when they're arranged like this and count the distance with your finger, this distance formula works for all cases where you have 2 points separated by some distance. So let me demonstrate that with this formula, you also get 4. We already know that the answer is 4, and based on our calculations here, we should get the same answer. Now, I would get yourself ready at the beginning by writing a shell for this formula. Put the minuses in the parenthesis, put the squares on the parenthesis, put the plus sign between them. This formula says that you're going to put your x's in one parenthesis and your y's in the other one. It actually doesn't matter whether you put the x's here and the y's here or vice versa, but you do need to get your x's, both of your x's in one parenthesis, both of your y's in one parenthesis. This x2, x1, it does not mean that you need to start with this point and move this way. You could start with these numbers and then go grab these numbers, or you can start here and then go grab those. I'm going to move this way. Okay, so in going to get my x's, if I'm moving this way, this would be my first x, this would be my second x. Okay, and then going to grab my y's and continuing to move in the same direction. This would be my first y, and this would be my other y. Okay, that y, that x2 and that y1, they're not dictating that you go in a specific order, but you do have to stick to the direction that you're moving in. So when you go to grab your x's, if you're using the numbers from this point first and then moving and grabbing the numbers from this point, you better stick to that when you do your y's as well, because that will make it come out wrong. Same direction both times. Okay, when you continue to simplify this, because you want to simplify this all the way until you have a single number underneath the square root symbol. You're going to keep simplifying it and simplifying it until you've accomplished that. So here we go. We're going to start whittling this down to a single number. Okay, in the first parenthesis with the square on it, 7 minus 7, that's 0. So that's going to be easy. Then here we have negative 7 followed by a double negative. A double negative gets replaced by a single positive. So in this next parenthesis, and you don't want to skip steps because that's what leads to making mistakes. It's negative 7 plus 3. Okay, remember, we're trying to work the inside of this square root, also known as the radicand. We're trying to work it all the way down to a single number. Do not take the square root before you have accomplished that. Okay, so let's continue. We have 0 squared. 0 raised to any power is just 0. So that, we're not even going to use that because it's just a 0. All we have left is really this. If you want to, you can write the 0. But this would be negative 7 plus 3, which is negative 4 squared. Okay, let's keep going. I'm going to continue it right up here. Okay, now when you put this in your calculator, if you are going to get the assistance of your calculator, you need to understand that you need to enter this exactly like it is since it's a negative, or else you're going to get a negative underneath your radical. And when you try to press that into your calculator, you're going to get an error. So if you are going to press this into your calculator, press it in with the parentheses and the square, or you can press it in, you know that anything squared is the number times itself. So if you do press it in like this, negative 4 times negative 4, that's one way to press it in. That's the same thing as negative 4 squared. However, if you're going to press it in as negative 4 squared, you know it's positive 16 because you cannot square and get a negative. But students that press it in improperly like this, negative 4, and then they put the square on it, they're going to get negative 16. And then when you go to take the square root of that, you're going to get an error because there's no such thing as the square root of a negative number. If you're going to enter a negative squared, you need to wrap it in parentheses. And then you'll get the positive 16 that you already know it is equal to. We just did it here properly. This is the improper way to enter it. So close that up. You should get positive 16 no matter how you're squaring, whether you're taking the number and multiplying it by itself, if it's a negative, or whether you're using the square function. If it's negative, wrap it in parentheses, or else you're going to get the wrong value. Okay, so this is really 0 plus 16. There was the word of warning that you are to work it until you have a single number underneath the radical, and that number better be positive. And then your very last step will be to take a square root. Okay, so now you can go in and you can go second square root, call up that square root symbol, tell it what you want to take the square root of, and you get a 4. Okay, so notice that with this formula, through a lot of steps, we got 4, but we also counted it with our finger. From -3 to here is 1 step, 2 steps, 3 steps, 4 steps, or 4 spaces. So we already knew just from counting that it was 4. Now the only time I'm going to keep emphasizing that you must use the distance formula in order to find out how, what the distance is between the points is if they are arranged on a slant. You can get away with just counting if they're like this, horizontally arranged. You can get away with just counting the spaces if they're vertically arranged, but not for this. You must use the distance formula if they are in this kind of arrangement. Okay, so you have 2 points like that, and they're on a diagonal. Must use the distance formula. But what I demonstrated in this problem is that you can find the distance if you want to, using the distance formula for any 2 points, even the ones where there's a shortcut, but obviously, why would you want to? Okay, so here you see that they have already plotted these 2 points for you, and you can see that they are spatially oriented on a diagonal. Okay, they're not horizontally across from each other, so you can't count the spaces. They're not vertically arranged, so you can't count the spaces. Okay, must use the distance formula here. So it's distance is equal to, let's get ourselves set up. We had one parenthesis where we were going to subtract our x's and then square it. Plus, we had another parenthesis where we were going to subtract our y's and then square it. You can move whichever way you want from this point to this point, or you can start here and move that way. Just make a decision, but stick to it. Stick to it both times when you do the x's and the y's, because if you switch up in the middle of the problem, then you're going to make a mistake. Okay, so I'm going to move this way. That's why I drew the arrow like this. I'm going to start here and end here with my x's as well as my y's. So if that be the case, if that's the decision I've made, my first x would be -8, and my next one would be -2. -8 and -2. Then as far as my y's go, again, moving in the same direction, this would be my first y, the 0, and my other y would be -5. Okay, from here, I'm going to clean this up all the way until I get a single number underneath the square root. Keep cleaning it up. Okay, let's keep rewriting it, each time getting closer and closer to a single number. First of all, in the first parenthesis, I have a double negative. They're both going to be thrown out and replaced by a single positive. So that parenthesis would now read -8 plus 2 with a square on it. In the other parenthesis, I also have a double negative. So both of those negatives are thrown out and replaced by a single positive. So I have 0 plus 5, still with the square there. Continue, trying to whittle this down all the way to a single number. Okay, right in here, let's actually, now that we don't have any more double signs, we go -8 plus 2. You can always put that in the calculator if you need to. -8 plus 2 is -6 with a square on it. I'm just doing one thing, getting a single number in the parenthesis. Let me do the same thing here. 0 plus 5, 5. Put a square on it. Continue. You're still underneath the square root. Okay, if you're going to put this in the calculator, put it in correctly. Open parenthesis, put the -6 in there, close the parenthesis, and then put a square. So this would be 36. And then you can also put this in the calculator. This would be 25. Keep going until you get a single number. This plus this would be 61. All of that still underneath the square root as we attempt to see what the distance is. Okay, let's round to the tenths place again. This is the exact answer. But if you are asked to approximate, as I am implying right now, to go to the tenths place, then you would put it in the calculator. So calling up the square root symbol, dumping in the number that I'm taking the square root of, and to the tenths place, that would be 7.8. The 8 is the tenths place. Okay, uncountable with your finger. You can't count the spaces here, so you have to know how to apply the formula. Okay, just a little bit about the distance formula. More applications of the square root operation that we were using on the previous page as well. Okay, that completes section 4.2.